Mechanical energy going to be the topic of this lesson in my brand new general physics playlist, which will cover a full year of university algebra-based general physics. Now, mechanical energy, simply put, is just the sum of both kinetic and potential energies. And to talk about these, we'll talk about both conservative and non-conservative forces. We'll also talk about the work-energy theorem, the work done by non-conservative forces, and definitely the conservation of mechanical energy as well. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. All right, so mechanical energy, simply put, is the sum of the kinetic energy and the potential energy. And these are the abbreviations we're going to use here. KE for kinetic energy, PE for potential energy. But you should know that these are not proper and not universally used by all textbooks. A lot of freshman physics textbooks will use them, but the proper ones are actually K and it turns out U. My personal preference is definitely KE and PE. It makes it much easier to remember what they stand for. But notice that your textbook may be a little bit different in that regard. But these are the ones we're going to use here. And we'll start with kinetic energy. This is the energy of motion. And in this case, it has a formula, 1/2 mv squared. Now, for the next several chapters, this is the only type of kinetic energy we will have presented. It's called translational kinetic energy, it turns out, and it's the energy of something as it undergoes motion through space. But we will learn another type later on, several chapters down the road, called rotational kinetic energy, involving rotational motion instead. But for now, when we say kinetic energy, for at least the next few chapters, we'll be specifically referring to translational kinetic energy, and you should associate it with this theorem. Now, if we take a look at that theorem there, we can see a couple different relationships. We can see that kinetic energy is proportional to mass. So you double the mass of an object, keep its velocity the same, and its kinetic energy will have also doubled. That's proportional. But we can also see that the kinetic energy is proportional to the velocity squared. And so in this case, if you double an object's velocity while keeping its mass the same, you haven't, well, let's get an E in there as well. So you haven't doubled the kinetic energy in that case. If you double the velocity, it's double squared. You've actually quadrupled the kinetic energy in that case as well. So a couple different relationships you should know there. Now, we also want to talk about potential energy. We'll find out it's kind of like the potential of being able to do work for an object. So before we can talk about that, there's a couple other terms we really want to introduce. And there are conservative forces and non-conservative forces. And all forces are generally going to fall into one of these two classes. Now, conservative forces get their name because if the only forces acting on an object are these conservative forces, then its mechanical energy is going to be conserved. And that's going to be a big highlight towards the end of this lesson, talking about the conservation of mechanical energy. However, if you've got non-conservative forces acting on an object, then its mechanical energy will not be conserved. All right, so if we look at if we just look at conservative forces, gravity is kind of the textbook example we give to you at this point. And so it turns out force is conservative if you move it from one point in space to another, and no matter which path you take, it's going to require the same amount of work. And gravity is a great case. If I move this marker from this spot to this spot, so because I'm moving it upward, it's going to take some work to accomplish that against gravity. Now, it wouldn't matter if I went directly there in a straight line or if I went like on a zigzag pattern at all to get this marker there. As long as I start in the same place and end in the same place, the same amount of work would be done as far as gravity is concerned. Now, we have what are called non-conservative forces that don't operate this way, and we usually think of these as being somewhat of what we call drag forces. Friction and air resistance are the most common examples. And these always oppose the motion. And so the longer your path, typically the longer they get to act, and the more they're going to decrease an object's mechanical energy, and therefore that mechanical energy is not going to be conserved. And along the way, whether it be friction, if you kind of look at rubbing your hands together, you can find that your hands warm up. And so these non-conservative forces take and convert some of the mechanical energy of an object either into things like heat or sound are the most common. And so as a result, an object is going to lose mechanical energy when these non-conservative forces are at work. And so again, going back to this path of the marker, as the marker moves on a zigzag path or something like that, or a straight line path, as long as there's not any significant amount of, say, air resistance or friction, so then we would say that only conservative forces are acting on it, and its mechanical energy is going to be conserved. The sum of its kinetic and potential energies would be conserved. And it wouldn't matter path. As long as I start in one place and end up in a second place, the path is independent if only conservative forces are acting on it. So those are those. So it turns out this idea of conservative forces, when these are possible and present, that is when potential energy is present. So it turns out gravity, so as I move this object up, it now has the potential to fall back down. And if it hits something, it has potential to do, say, work as it comes into contact with some other object, like, say, pounding a nail in. Whether I pound a nail in with a hammer or whether I drop the marker and it hits the head of the nail, if it's moving fast enough, it might pound it in a little bit too and do some work on that nail. And so potential energy is kind of the potential to do work, and potential energy is possible when there are these conservative forces like gravity, or we'll see the electrostatic force in the next semester and things of that sort. And so potential energy, the only working version of potential energy we'll talk about right now is called gravitational potential energy. And it turns out it's equal to mass times gravity times the height. Now, some books will use an h right here, and it's personally my preference is to use h as well, but we'll use y. So it's probably a little more common in most textbooks these days. And so y refers to the height above some, level. And oftentimes the zero level is kind of often ground level, but it might just be the lowest possible point on some object's trajectory. So if I throw this marker, and it comes down and hits the ground, we might call the ground level 0. But if I'm on top of a skyscraper and I throw this marker and then it just lands still on the roof of the skyscraper, well, then I might call the top of the skyscraper the 0 level. It's kind of arbitrary. And what we're going to find out is that the change in height is really the important thing. But typically the lowest point in the trajectory is going to be the 0 point, and that's quite often the ground. All right, so for potential energy, a couple different relationships here as well. We can see that potential energy is proportional to an object's mass. You double the mass, you double its potential energy. It's also proportional to the height. So double the height and you double the potential energy there as well. Now, technically, it's proportional to gravity as well. But most of the examples you're going to be discussing are just going to be on the surface of the Earth. And on the surface of the Earth, that gravity, the acceleration due to gravity, 9.8 meters per second squared, is going to be constant. Now, if you move to the moon, where there's only 1/6 of the gravity, well, then we're going to find out, yeah, that would definitely affect the potential energy as well. But for most of the cases you're going to see, we're going to be at the surface of the Earth. And so gravity is going to be constant in those cases. All right, so we got a couple other things to talk about. The next one is what we call the Work-Energy Theorem. And it talks about when there's a net amount of work done on an object. And so it turns out when you do net work on an object, it's going to change its kinetic energy. So it will either move faster or slower depending on if it's net positive work or net negative work. But if you don't do net work, if there's no net work, if the net work is 0 joules, if you will, or just simply 0, then the kinetic energy is not going to change, and that object's velocity is going to remain constant. So it works both ways. For example, let's say we take this lovely marker right here. And let's say I raise it up at constant velocity or I lower it down at constant velocity. Well, because this is being done at constant velocity in either case, there should be no change in kinetic energy. Velocity is constant, right? So if the v stays constant and the marker is not changing its mass, well, then kinetic energy is going to remain constant, and this change in kinetic energy should be 0. Which means the net work should be 0, and that's exactly true. So let's consider the case where I'm raising it up. Well, as I raise it up at constant velocity, because it's at constant velocity, there's no net force, no net acceleration, and so what you find is that there's an upward force, which is the pushing force on my hand, or you might call it a normal force from my hand, but then there's also gravity pointing down. Now, because I'm moving upwards, the force of my hand and the displacement both point up, and that's going to be positive work. But it turns out the force I'm going to have to apply with is going to have to be perfectly balancing out the weight, which points down. And so as I move up, the weight still points down, but the displacement points up, and that's going to be negative work. And it turns out the positive work being done by my hand is exactly equal to the negative work being done by gravity. And that's why the net work is going to be 0, and why the change in kinetic energy will also be 0. Now, on the other hand, let's say instead of having, constant velocity here. So let's say instead the force that I'm pushing up with my hand and the force that gravity is pulling down with, i.e. its weight, are not equal. And let's say that, the force of my hand is greater. And so instead of moving up at constant velocity, all of a sudden now, because there's an overall net upward force, because again, the force of my hand going up is bigger than gravity going down, then all of a sudden this thing's going to accelerate upward, at least as long as it's in contact with my hand. And while it's accelerating upward, we can see then, oh, Well, now the force upward, which is in line with the displacement, is bigger than the force downward, which opposes the displacement. And so the work pointing up is going to be larger, again, force times displacement, since it has a larger force than the work going down. The work going up was positive, the work going down was negative, and so all of a sudden now there's a net positive work. And if there's a net positive work, then we're going to see a positive change in kinetic energy, an increase in this case in kinetic energy, increase in velocity. So that's kind of how that works. That's that work-energy theorem. So if you know all the forces acting on an object, and you can kind of calculate all their contributions, if you will, that they would contribute to the net work, then you could figure out the net kinetic energy. Or vice versa. If you can figure out what the change in kinetic energy is going to be, then you could figure out what net work must be being done or performed on an object. All right, next we'll move on to talking about these non-conservative forces. Now, we're going to find out in a little bit here that conservation of mechanical energy, that's true, again, when there's only conservative forces acting on something. That's how we kind of jumped into this in defining conservative forces. So now if you have non-conservative forces, though, it's not going to be true. And you're going to find out that the work done by non-conservative forces is always negative. They always oppose the motion. And because they're always opposing the motion, well, force and displacement are in opposite directions. That's negative work. And again, non-conservative forces always are in the opposite direction to the motion. And so the work they do is always negative. And they always, therefore, decrease the total amount of mechanical energy. Well, it turns out that the work done is going to be equal to the sum of the change in the kinetic energy and the change in the potential energy, or simply put, it's going to equal the change in the mechanical energy. So whenever you have non-conservative forces going on there, it will be a negative sum because they're always going to be decreasing the total amount of mechanical energy. So when we have only conservative forces, we're going to find out that the mechanical energy will be conserved, but when we have non-conservative forces, we're going to find out that the mechanical energy is going to decrease, corresponding to a negative amount of work done by those non-conservative forces. And then finally, we'll talk about the conservation of mechanical energy here. So, and it just simply says that for an object only experiencing conservative forces, no non-conservative forces, that the kinetic energy initial plus potential energy initial will equal the kinetic energy final plus potential energy final, totally conserved. Now we could expand this out just a little bit. So, and we could say that 1/2 mv initial squared plus mgy initial equals 1/2 mv final squared plus mgy final, and expand it out that way. What you're going to find out, though, is that I usually prefer writing it out the first way first when doing certain calculations involving the conservation of mechanical energy. And the reason being is you're going to find out that oftentimes, so out of these four terms, one or more of them are going to equal 0, either in the initial or final conditions. And so you're going to be able to just cross them out. And so why write out the expanded version and write out a bunch of stuff if you're just going to lose some of those terms because they are 0 in such cases? So, but take your pick. Whether you want to represent it this way or this way, it is up to you. We'll work some problems. You'll see kind of how it presents itself. All right, and now we're ready to present some problems. So we've kind of set up a conceptual framework, introduced some equations, and now we're kind of ready to do a random assortment of problems that are going to kind of give examples of all of these. So we'll start with the first one. A 1,000.0 kilogram car has a velocity of 20.0 meters per second. What is its kinetic energy, and then how much net work must be done to bring the car to rest? All right, so we want the kinetic energy first. You know, in fact, let's make a little room here. We can see that kinetic energy is simply equal to 1/2 mv squared. And we can just plug and chug. So we're told it's a 1,000.0 kilogram car moving at 20.0 meters per second. Don't forget to square that. That's one of the more common errors students will make in this section. It's just they write out the equation and they just forget to include the square, and then they forget to include it in the calculation. So, and I was about to pull out the calculator, but we can probably do this one in our heads as well. So 20 squared is 400. 400 times 1,000 is 400,000. Times 1/2 would be 200,000. And so in this case, our kinetic energy is going to equal 400,000 joules. Now, it's not uncommon, especially if you're getting like a multiple choice question, it's not uncommon to see answers, especially for very large numbers of joules, expressed in kilojoules. And so potentially you could also see this, to convert to kilojoules, we divide by 1,000, and so you could also see it as 400 kilojoules. Now we got to worry about sig figs here for a second. So this guy's definitely got a large number of sig figs, 5. This guy's only got 3. We're gonna need 3 sig figs here. Well, that's a pain in the butt with a bunch of zeros, and I really prefer not drawing lines over zeros most of the time. And so I prefer to write in scientific notation. So in this case, I'm gonna make this one 4.00 times 10 to the 5th joules. So 1, 2, 3, 4, 5 decimal places moved. So times 10 to the 5th, since it's a number bigger than 1, it's a positive power of 10, or since I moved the decimal to the left, however you look at it. So same thing over here. We're going to make this one 4.00 times 10 to the 2nd kilojoules. So, and again, writing them in scientific notation, my preferred way to get the proper number of sig figs rather than trying to put a line over some zeros to show that they're significant and things of that sort. Cool, so that's the first half of this question. Second one, though, is how much net work must be done to bring the car to rest. So it's got initial velocity of 20 meters per second. We're trying to bring it to rest, i.e. where its velocity is 0. And this is where that work-energy theorem comes into play. And the key is, if you notice, it said net work right in the problem, and that's what's in the work-energy theorem. So, and we're doing a change in kinetic energy. We're taking it from 20 meters per second velocity down to 0. This is exactly what this theorem is made for. And so in this case, work net is equal to that change in kinetic energy, which we might simply write again as kinetic energy final minus kinetic energy initial. And so if you look here, well, we want to end up at rest, which is the final amount of kinetic energy of 0. If you plug a 0 in for velocity, you'd get 0 kinetic energy. They're proportional, or at least proportional to the square, but still 0 is going to get you 0. And so in this case, that's a zilch minus the initial kinetic energy. Well, we could go back and figure that out again, but we already did, right? We already got the 400 kilojoules or 400,000 joules in there. And so in this case, I'll make it 4.00 times 10 to the 5th joules. And 0 minus that gets us a negative number. Negative 4.00 times 10 to the 5th joules for our net work. And does it make sense that it's negative? So again, when we do net work here, that's negative, this means the object is slowing down. And indeed it is. It had initial velocity of 20 meters per second. It ends up at rest with no velocity. That definitely corresponds to a loss of kinetic energy and therefore negative work being done. So when work net is negative, the object is slowing down. When work net is positive, that object is speeding up instead. Let's take a look at another. Okay, so the next question here says, a stone is dropped from a height of 7.35 meters. What is the final velocity just before it reaches the ground? And this problem should look somewhat familiar. It's a kinematics question, right? And so you could totally solve this using kinematics. But a lot of students struggle with kinematics more than what we're about to do. So notice it even says ignore air resistance at the end of the problem. And if we're ignoring air resistance, a non-conservative force, this would mean we only have conservative forces acting on it, and the conservation of mechanical energy is going to apply. What's nice is there's only one conservation of mechanical energy equation. Now it turns out, later on we're going to find out that we can add some like rotational kinetic energy terms, and we can add other types of potential energy into there as well. So it can get a little more complicated, truth be told, but it's still in principle just one equation. So that the initial amount of kinetic and potential energies is equal to the final amount of kinetic and potential energies. Whereas with kinematics, again, we had at least 4 equations, and students often struggle, which one do I use, in which situations, and things of this sort. And if you did, you might find that there's a number of kinematics problems that are now much easier to solve with the conservation of mechanical energy. So let's see how this works. So in this case, again, we've got kinetic energy initial plus potential energy initial, let's get that right, equals kinetic energy final plus potential energy final. So, and before we expand this out, let's just take some things into account here. So initially it's dropped from rest. And if it's dropped from rest up here, then it has no velocity and therefore no initial kinetic energy. So, and again here, the lowest point in its trajectory is the ground level. And so we'll probably define the 0 height as ground level. And so right as it's hitting the ground at the very end, its height is 0. And so its potential energy with a height of 0 is also going to be 0. And that's the final potential energy. And so here we're left with a situation where the initial amount of potential energy is going to equal the final amount of kinetic energy. And so we can substitute our expressions in. So mgy initial equals 1/2 mv final squared. And notice what falls out. Mass falls out of this, which shouldn't be too surprising. The only conservative force we have acting on this object, and the only force in general, is gravity. And gravity doesn't care about your mass. If you recall, we said if you drop a feather and a bowling ball, well, we know the bowling ball is going to fall faster, except that's due to air resistance. If you did that inside a vacuum or on the moon where there's no atmosphere, they would fall together all the way down. And the acceleration in a vacuum on Earth, surface of this would be 9.8 meters per second squared. On the moon, it would be a little bit less, or quite a bit less. So, but they would fall together and accelerate together would be the key. And so we shouldn't be surprised that mass is going to fall out of this equation here with gravity being the only force acting. And so if we go ahead and solve for velocity here, we're going to get v final squared equals, so multiply by 2, so do g yi, and then we'll take the square root of both sides. So 2 times 9.8 meters per second squared times, and in this case, again, our initial height was at 7.35 meters. Cool. Now, it turns out this is a fairly common result. And it turns out if something is dropped from rest, some people actually teach the equation that the final velocity will equal the square root of 2gy, or 2gh. So I hate just memorizing equations that apply in certain situations. I really like just setting up how to solve the problem from first principles, like setting up conservation of mechanical energy, things of the sort. So, but if you've been taught to memorize that, fair enough. All right, so here we've got the square root of 2 times, so let's put this all in parentheses, square root parentheses 2 times 9.8 times 7.35. I'll close those parentheses, and we're going to get 12.0025 meters per second, which I'm going to round to, let's see, how many sig figs? We're going to round that to 3 sig figs. That's going to be 12.0 meters per second. Okay, so let's take a look at this just a little bit different way. How might we have solved this using kinematics in this case? In this case, following a height of 7.35 meters, we might have said, well, we don't know anything about how long this thing is falling, time, and so perhaps we would have used v final squared equals v initial squared plus 2 times a times delta x. And this is how we would have solved this back with kinematics. And we would have said, we want that final velocity squared. The initial velocity, though, was 0, and that falls out. And notice what happens here. You're going to take the square root of both sides, and you're going to have 2 times the acceleration, in this case due to gravity, 9.8 meters per second squared, and then times the displacement, which was 7.35 meters, and it ends up with the same exact calculation, which obviously is going to lead you to the same result of 12.0 meters per second. So, but again, a lot of students would struggle getting to the point of like, which of the kinematics equations do I use? So, whereas again, in the context of conservation of mechanical energy, there's only one equation. Life is good. All right, so our next question here says a baseball is thrown straight upward in the air with an initial velocity of 50.0 meters per second. What is the maximum height reached by the ball? Ignore air resistance. And again, this is going to look a lot like a kinematics problem. And again, you could totally solve this with kinematics. Or we could take into account that we're told to ignore air resistance, there's no non-conservative forces, and so the conservation of mechanical energy should totally apply. Now, if we take a look at the entire trajectory here, so this thing is going to be slowing down, slowing down, slowing down until it reaches its maximum height here. And at that point, so its final velocity is going to be 0. And that's going to be basis here. So here we're going to be at a maximum of kinetic energy. Up here, we're going to be at a maximum of potential energy. In fact, at its initial point, it's all kinetic energy because it's at a height of 0. And at the end, it's all potential energy because its velocity is 0, and therefore its kinetic energy is 0. And it's similar to the setup we just had in certain respects. So, but we set it up the same way. So kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. And taking into account what we just said, so initially it has no height, so its potential energy is 0. And at the end of the top of its trajectory, when it reaches the max height, that's when its velocity and therefore kinetic energy is 0. And so in this case, our kinetic energy initial, 1/2 mv initial squared, is going to equal our final potential energy, mgy final. Cool, and from here, it is some plugging and chugging. Now, before we process this, though, let's see how we've approached this with kinematics. Well, again, 50 meters per second, initial velocity. It's going to be slowing down by 9.8 meters per second every second due to gravity, right? So, which is roughly 10 meters per second. And so after 1 second, it's going to be slowed down to like 40 meters per second. After a second, down to 30 meters per second approximately. And so it's going to take roughly 5 seconds for its velocity to slow down to 0 from what we learned at kinematics. Okay, so it's a 5-second journey for the way up. Its initial velocity is 50 meters per second. We know its final velocity is 0. It's really easy to see that the average velocity, therefore, is 25 meters per second. 50 plus 0 all over 2. Well, an average velocity, if you recall, we had displacement equals average velocity times time was one way we did that. And so an average velocity of 25 meters per second times 5 seconds would be roughly 125 meters. And so that's what I'm expecting to get here when we do this calculation. Now, it's not going to be exactly 125 because, again, we said, well, gravity's about 10 meters per second, but it's really 9.8. But it should be in the ballpark here of roughly 125 meters as verified with our kinematics version of this calculation. So let's do some plugging and chugging here. Notice what conspicuously falls out again is the mass. So, and in here, we actually want to figure out, again, that max height. So which is going to be YF there. So in this case, we're going to have 1/2 V initial squared all over G, getting us that max height. So, and that initial velocity was 50.0 meters per second. Don't forget to square it. And again, all over 9.8 meters per second squared gets us our final height, which is the max height. And once again, we can ballpark this in our head. So 50 squared, well, 5 squared is 25, and add 2 zeros onto that. So 2,500. 2,500 divided by roughly 10 would be 250, and 250 times 1/2 would be 125. And so we can see this is going to come out to roughly 125 meters, just like we thought it would. But let's get an exact number on there and round it to 3 sig figs. So we're going to have 0.5 times 50 squared, don't forget to square it, divided by 9.8, and we're going to get 127.55, so we'll round that up to 128 meters for 3 sig figs. Cool. And again, a lot of students really prefer using the conservation of mechanical energy than those old kinematics equations. Now, there are going to be places where the kinematics equations are more convenient or where the conservation of mechanical energy doesn't apply or won't work. So, but for many of the kinematics problems, this conservation of mechanical energy might be a godsend for some of you. All right, so the next question says, a 10.0 kilogram box slides from rest down a 5.0 meter long frictionless ramp inclined 30 degrees above the horizontal. What is its final velocity at the bottom of the ramp? Okay, now we could again use some kinematics or some Newton's laws of motion and the combination thereof to figure this out. We could set up a free body diagram and figure out that the component of this object's weight down the incline is mg sine 30. So, and then set mg sine 30 equal to ma according to Newton's second law, solve for that acceleration, and then figure out how long does it take to go 5 meters, which would be a lot of work. Or we could realize that, again, there's no friction here. And because there's no friction, so then there's no non-conservative forces, and the conservation of mechanical energy is going to apply. And you might be like, but Chad, this thing isn't falling straight down. And conservative forces don't care. They don't care about the path. As long as we go from one height to another height, it doesn't matter what path you take to get there. And so the only thing that matters is the change in height. And in fact, it wouldn't matter if we went straight down falling or falling down the ramp, but ending up at this height compared to this height. That's all that ultimately matters. Now, if we take a look at this, then conservation of mechanical energy, kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. And again, this thing is starting from rest. If it's starting from rest, then its initial velocity is 0, which means it initially has no kinetic energy. cool, the lowest part in its trajectory is when it gets to the bottom of the ramp. And so we'll call that the zero line. And so at the end, it has no height. And so at the end, it has no potential energy. Now, one thing to note here, we're taking the extremes here because it's really convenient here and relevant to this problem and stuff. So, but we're getting that the initial potential energy equals the final kinetic energy. But again, one thing you should realize anywhere along this trajectory is that the kinetic and potential sum will always be the same when we have the conservation of mechanical energy. So even if we were in the middle of the trajectory here, so in the middle, it would have both some kinetic and some potential, but the total between these two would equal the same total we're going to get here or the same total we're going to get here. It's always the same when there's only conservative forces acting on the object. Okay, so all the way down that ramp, it's going to be getting faster and faster and faster, and so its kinetic energy is going to be going up. But all the way down the ramp, its height is getting lower and lower and lower, and so it's going to be losing potential. But the sum of the two will remain constant all the way through. All right, so set this up then. We've got mg y initial equals 1/2 mv final squared. And this should look a little bit familiar. We'll see it that the mass falls out yet again. Whether you're on a ramp or not, gravity doesn't care about your mass, as long as there's only conservative forces acting on it. All right, so in this case, solving for that final velocity, this should look familiar. 2gyi, take the square root. And there's our plug it and chugging, but we got to know what that initial height was. Well, we know the ramp is 5 meters long, but we don't actually have the height above kind of the ground level, zero level here in this case. So we got to figure that out. And so you're gonna have to remember a little bit of your trigonometry here. So if you notice, this is the side that is opposite the 30 degrees. And so sine of 30 would equal opposite over hypotenuse. In fact, let's write that out. So sine of 30 degrees equals opposite over hypotenuse. Well, it's the opposite side that we want. And we can see that it equals hypotenuse times the sine of 30 degrees, which in this case is going to be 5 meters times sine of 30 degrees. Now, I like using 30 degrees in practice problems quite a bit for lecture presentation because it's nice convenient. Sine of 30 is 1/2, and 1/2 times 5 is 2.5 meters. So, but obviously this could be any angle, but for purposes of presenting a lecture, it's just nice using numbers that come out nice and round like that. All right, so we'll get the square root of 2 times 9.8 meters per second squared times a height of 2.5 meters, equaling our final velocity, and we'll let our calculator go to work for us here. So once again, we'll take the square root, parentheses 2 times 9.8 times 2.5. I'll close out those parentheses. And it doesn't like my syntax. Let's try this again. What did I do wrong? Oh, I used the wrong bracket at the end. All right, that's going to get us, oh, I made the math nice here. Comes out to exactly 7 meters per second. So in this case, we're limited to 2 sig figs by the 5.0 meters, and so we'll make this 7.0 meters per second. Okay, so the next problem's a little bit related to this one. So it starts off, a 10.0 kilogram box slides down a 5.0 meter long ramp, inclined 30.0 degrees above the horizontal. If the velocity of the box at the base of the ramp is 6.0 meters per second, not 7, 6.0 meters per second, how much work was performed by non-conservative forces on the box? So here's the deal. If it only has a velocity at the bottom of 6 meters per second, again, if mechanical energy is conserved and the conservation of mechanical energy applies, we just figured out it would be 7.0 meters per second. Well, now in this next example, it's only 6. And so we can see that, oh, mechanical energy was not conserved. When is mechanical energy not conserved? Well, when there are non-conservative forces at work. And how do you calculate the work of those non-conservative forces? If you recall, we always said it's negative. They're always going to lower the total mechanical energy, and it's just equal to the change in mechanical energy. All right, so at the top of our trajectory here, we have some amount of kinetic and potential energy. So, and then at the bottom here, again, we're going to have some amount of kinetic plus potential energy. But because gravity is doing work in this case, I'm sorry, not gravity, because friction is doing work here and opposing the motion, we should expect this to be lower. And again, the difference between these two will be the work done by friction, in this case by non-conservative forces. And that work will be negative. And so with our change, we'll call this, we can use initial and final in this case. So our work is therefore going to equal the change in mechanical energy, which we could look at as change again in kinetic plus change in potential, which would be kinetic energy final. Well, let's get that E in there. Kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. Now again, because we already have the difference in the final kinetic energies with and without this friction, 7 meters per second velocity would allow us to calculate kinetic energy in one case, 6 meters per second in the other case, we could just take the difference in life and be good. But had we not already performed that problem, this is where we'd be going with this, in this work done by the non-conservative force of friction. And so if we take a look at this, so kinetic energy initially is a big fat zilch. It's dropped from rest. So that term is 0. So, and then the potential energy finally is 0. And so we can eliminate some of these terms here. So in this case then, our work done by non-conservative forces is going to equal 1/2 mv final squared plus mg y initial. Oh, there's a minus, huh? Because it's plus minus plus a negative. So we'll subtract that off. All right, so let's do some plugging and chugging. So notice, does mass fall out of this equation, by the way, like it's done before? Well, mass is here, mass is here. Can't we just take it out? Well, no, we can't in this case. If we could factor it out, but we can't actually remove it because it's not equal to 0 on this side. So mass totally matters. It hasn't mattered in the past. It totally matters now. And so we'll need that 10.0 kilograms now. That final velocity in this case was 6.0 meters per second. Don't forget to square it. Minus again 10.0 kilograms times gravity. 9.8 meters per second squared. And that initial height, again, was that 2.5 meters, that 5 sine 30, if you will. Cool, and we can do some plugging and chugging from here. All right, so 0.5 times 10 times 6 squared minus 10 times 9.8 times 2.5. And we're going to get negative 65 here in this case. And that is joules. And we need 2 sig figs based on the 6.0 meters per second and the 5.0 meters. And that is 2 sig figs. So there's your work done by friction. It came out negative, just like we expected it to for a non-conservative force. And life is good. Now, a couple other things to look at here. So not the only way we could have approached this problem. And a lot of students would have said, well, work done by friction in this case. Well, work is force times displacement. And they would have looked at this and said, oh, okay. Well, work is force times displacement. So in this case, the force of friction is normal force times the coefficient of kinetic friction in this case. And they would have said, oh, the normal force is equal to mg cosine 30. Great. But the coefficient of kinetic friction is not given. And at this point, some students might be inclined, if this was on an exam, to go up to the professor like, hey, you didn't give us the coefficient of kinetic friction. At which point your professor would say, I didn't need to. Go back to the drawing board. Because that would be one approach to take at this. There's more than one equation now we've learned that have work in it, and that one wasn't going to work. Force times displacement wasn't going to work because we had no way of actually calculating the force due to friction without the coefficient of kinetic friction being supplied. So just one thing to keep in mind. One other thing to take a look at here real quick. So just a couple things. So if we take a look at that initial total mechanical energy, the kinetic and potential combined. Again, that initial kinetic was 0. But the potential here was the 10 times 9.8 times 2.5. And let's work that out one more time. So 10 times 9.8 times 2.5. And that's 245 joules. So initially, the total mechanical energy, which was all potential, was 245 joules. Now at the end, it's all kinetic and none potential, because we're at a height of 0. And it was the 1/2 mv squared. And so in this case, 6 squared is 36 times 10 to the 360 times a half is 180. And so at the end here, this total comes out to 180 joules. Well, the work done by the non-conservative forces just equals the loss of mechanical energy. And you might be like, well, how much mechanical energy would we lose? Well, from 245 joules down to 180 joules, we lost 65 joules. And the work done by the non-conservative force is that negative, you got to make sure it's negative, negative 65 joules. So just another kind of conceptual way to look at it instead of just like, I just plugged and chugged in equations. So you just understand that, oh, we had so much mechanical energy to begin with, we didn't end up with the same amount. Mechanical energy was not conserved, and so there must have been some work done by some non-conservative forces. And it's the difference of the two. And again, if you do final minus initial, that's how you'll get it to come out negative if you want a formula, or you can simply remember that it's the difference between the two, but it has to be negative for the work done by a non-conservative force. If you have found this lesson helpful, consider giving it a like. Happy studying.